Hi everyone, I'm Vahid. I'm a data scientist and a machine learning researcher. In this video, I like to explain different activation functions so that we can understand how these different functions behave, what their derivatives look like, and finally a few points like their use cases and applications. Here are the 10 activation functions that we are going to study in this video. The table on the left are the 5 most commonly used activation functions, and the table on the right are slightly more advanced activation functions. We are going to go through each one of them and look at their behavior. So let's get started. Our first activation function is a linear function, or simply f of x equals x, which means it will output whatever was passed to it as input. So let's plot this function and see how does it look like. Here is the graph of the f of x equals x, and as you can see, it's just a straight line that passes through origin with a slope of 1. And its derivative is also a constant value of 1, because the slope of this linear function is 1. This simple function is not very useful in artificial neural networks because it does not do anything to our data. Usually, when we are designing artificial neural networks, we want to have some form of nonlinearities between consecutive layers of the network. So next, we are going to see some nonlinear activation functions instead. The next activation function is ReLU, which stands for Rectified Linear Unit. ReLU is a nonlinear activation function, and it can be represented mathematically in different ways. One way is to use the if condition on the values of x as shown on top, and the other way is simply using the max function as shown in the bottom. Now let's explore the graph of the ReLU function. As you can see here, it outputs 0 whenever the input x is negative, but when x is positive, it will output the same x. The derivative of ReLU is also very simple, and it is shown in the red graph. As you can see, this derivative function has two disconnected regions. When x is negative, the derivative or the slope of ReLU is 0. And when x is positive, the slope is 1. And note that it is not differentiable at origin or x equals 0. ReLU and its variants are very popular in building neural networks for adding nonlinearity to network layers. One advantage of the ReLU activation is that it results in sparse models. So neurons that have negative pre-activation values will be turned into 0 by the ReLU activation, and this will make the model sparse. But the drawback of ReLU is that once a neuron activation becomes 0, that particular neuron can no longer affect the parameters of the network effectively, because the gradient of that neuron activation is 0, and 0 multiplied by any value during backpropagation and the chain rule would still be a 0. Our next activation function is the Leaky ReLU, which is a modified version of ReLU, or we can say it is a ReLU variant. Here, instead of having a flat 0 for the negative input values, we have a straight line with a small slope as indicated with alpha times x. So alpha is the slope of that line, and this alpha can be between 0 and 1. And here we can see how the graph of the Leaky ReLU look like. So it's basically somewhere in between the linear and the ReLU function. If alpha approaches 0, the Leaky ReLU function will approach the behavior of the ReLU function. And when alpha gets closer to 1, it will behave similar to the linear function. Now, the derivative of the Leaky ReLU is also a discontinuous function. When x is negative, the slope is alpha, and when x is positive, the slope is 1. And note that it is not differentiable at origin. And now we reach our fourth activation function, which is the logistic sigmoid function, or aka sigmoid. The sigmoid function is a smooth version of the step function, and it is mathematically defined as 1 over 1 plus e to the power of negative x. The output of sigmoid can be anywhere between -1 and 1, as it is shown in this graph as well. And its derivative is also written as sigmoid of x minus sigmoid squared of x. After we observed that the derivative of ReLU and Leaky ReLU were discontinuous functions, now instead we have a function that its derivative is continuous. This derivative function has a peak at the origin, x equals 0, and the two tails, both from left and right, approach 0. It is very important to note that the sigmoid function at its two tails may get saturated. That means when x becomes a very large positive number or a very large negative number, the sigmoid becomes saturated. And as a result, the derivative of sigmoid approaches 0. This is also called the vanishing gradient, which is a common problem in training artificial neural networks. But nevertheless, sigmoid is typically used in the last layer of neural networks for binary classification. Besides that, it is also used as the gating mechanism in recurrent neural networks, such as LSTMs and the GRUs. Our fifth function is the hyperbolic tangent, or tanh for short. Tanh is defined as exp of x minus exp of negative x divided by exp of x plus exp of negative x. And as you can see in the graph of tanh shown in yellow, its output ranges between -1 and 1. So next, let's take a look at the derivative of tanh. You can see the formula written in red, but also the shape of the derivative of tanh is very similar to the one for sigmoid. It has a peak in the center or origin and the two tails that zero out. Note that the slope of the derivative of tanh is steeper than the one for sigmoid, and therefore it has less problems with the vanishing gradient. Tanh is sometimes used as a nonlinear activation function in hidden layers of neural networks, but it is less common than the ReLU family. Its special application is in recurrent neural networks, such as the LSTM and the GRU. Now we reach the more advanced activation functions. But before we start with the Softplus, let's recap one of the problems with the ReLU family, either ReLU or the Leaky ReLU. If you recall, the problem with ReLU and Leaky ReLU was that they are not differentiable at origin, or x equals 0. And in fact, they have these discontinuous derivative functions. Softplus is a smooth version of the ReLU function, and it is differentiable at the origin. It's mathematically defined as the natural log of 1 plus e to the power of x. And as you can see in the graph shown in yellow, it doesn't have that sharp turn at x equals 0, because sharp turns of ReLU will make it non-differentiable. But here we have a smooth curve which makes it differentiable. Now, taking the derivative of the Softplus function, we get e to the power of x divided by 1 plus e to the power of x. But you can rewrite this function by multiplying both numerator and the denominator by e to the power of negative x. And this will result in 1 divided by 1 plus exp of negative x. And this function is familiar to us. That is our sigmoid function, or the logistic sigmoid. So to summarize, Softplus is a smooth version of ReLU, and its derivative is the sigmoid function. Next, we have the elastic linear unit, or ELU. This function is defined using a condition on x. When x is positive, the result will be x itself, so no change. And when x is negative, the result of ELU will be alpha times the exp of x minus 1. Now let's see how the graph of ELU look like. As you can see in the graph shown here, ELU approaches -1 when x goes to -infinity. Note that this graph is plotted for alpha equals 1. And for alpha equals 1, if you look carefully at the origin, you will see that the slope of the curve is smooth, before and after 0. So that means the derivative of ELU is a continuous function. This can also be confirmed in the graph of the derivative of ELU. But note that this is only the case when alpha equals 1. If alpha is something other than 1, then ELU is not differentiable at origin and the derivative will be a discontinuous function. The next activation function is a scaled exponential linear unit, or SELU. SELU was proposed in a 2017 paper titled Self-Normalizing Neural Networks, which basically tries to converge the neuron's activations toward zero mean and unit variance. The mathematical formula of the SELU function is very similar to the one for ELU, except that it has a lambda factor that affects both regions, positive and negative. And the proposed value for lambda is 1.0507 and alpha is supposed to be 1.6732. As you can see, the graph of SELU is also very similar to the graph of ELU. But looking carefully at x equals 0, we can see that there is a sudden change in the slope of the curve before 0 and after 0. This is because alpha is not 1 anymore, and it makes the slope of the curve for the region before 0 and after 0 to be different. As a result, SELU function is non-differentiable at x equals 0, and the derivative of SELU is a discontinuous function. Our ninth activation function is the Swish function, which has outperformed both ReLU and the sigmoid in several applications. Swish is mathematically defined as the product of x times sigmoid of beta times x, where beta is a learnable parameter. Note that sometimes you may observe that parameter beta is omitted, which in that case it means it is implicitly set to 1. And if that happens, sometimes it is called the sigmoid linear unit, or SELU. The graph of the Swish function with parameter beta equals 1 is shown here. One property of the Swish function makes it different from all our previous activation functions, and that is the Swish function is a non-monotonic function. So what is a monotonic function? A monotonic function is a function that is always non-decreasing or it is always non-increasing. In other words, a monotonically increasing function is a function that as you increase x, the value of that function will either increase or stay the same, but it will never decrease. And a monotonically decreasing function is the opposite, where as you increase x, the value of that function will either stay the same or decrease. But here for the Swish function, we have a non-monotonic function. The reason is, in the beginning, going from left to right, we can see that at first, the value of the Swish function will decrease until it reaches a minimum, and then from there it starts increasing. That makes it a non-monotonic function. Now, the derivative of the Swish function is shown in red, and as you can see, it is a continuous function. However, because the Swish function is a non-monotonic function, the derivative of the Swish function has both negative and positive values. And for the last function, we have GELU, which stands for Gaussian Error Linear Unit. The mathematical formula of GELU is rather long, as you can see here. So we cannot make any sense of this long equation. So let's instead look at the graph of GELU to understand its behavior. Now we can see clearly that the GELU function is also a non-monotonic function, similar to the Swish function. As we trace this function from left to right by increasing x, GELU starts with a flat region, like almost flat region, and then takes a downward slope until it reaches its minimum. After that, it picks up and starts increasing and passes through the origin. So because it has both decreasing region and an increasing region, it makes it a non-monotonic function. The derivative of GELU also has both negative and positive values as shown in the red graph. GELU is used in large language models such as BERT or GPT-2. That's it for the 10 commonly used activation functions in neural networks. If you have any comments or questions, please feel free to put your comments down below, and thanks for watching.